parameterization. Because you remember, we are imagining having a situation, say, in which you have, I don't know, an integral over the plane, and then some gauge fixing condition, and you want to sort of, which use the scaling symmetry, eliminate the degree of freedom of the scaling symmetry, and reduce yourself to an integral over the gauge fixing, or the submanifold of your space defined by the gauge fixing condition. And we look at gauge fixing conditions, say of this form, some equation, some expression of your elementary degrees of freedom that you would like to be 0. Okay? And so we explain you can take your delta function of f, and then dress it to the Jacobian, etc., etc. Now, suppose that somebody else had given me the gauge fixing condition not as an equation satisfied by x and y, but in a parametric form. So somebody could have told me, I want you to only integrate over the x's and y's such that some relation like this is true for some t. So this is like a parameterization of this gauge fixing condition in terms of some extra parameter t. Or perhaps they might have said, okay, set some equations like this to 0. So you're adding some extra degree of freedom whose only purpose is to write down your gauge fixing condition. Okay. So how do you deal with something like that? Well, it's not terribly difficult. We do exactly what we've done before for quantizing this system. So we have these delta functions. I want to test them with the Jacobian, and then write it in terms of an integral over ghosts. So in terms of the sort of the topological theory that you add to do this, so we had, this sort of pairs for the gauge fixing conditions. We had ghosts for every degree of freedom. So what you could do is simply to add some ghost for this extra degree of freedom, where Qt is theta, say. And then write the usual kind of action, e to the IB, IFI of XGT plus C, so DI, D, A, F, CA plus DI, DA, F, D, EF, theta. Okay, so I did nothing strange. I'm just treating T the same way I was treating my other degrees of freedom. And finally, if I really want, if these T and theta were sufficiently simple parameters, I might want to just do the theta integral. See, this T and theta only appear in the gauge fixing condition. This T appears only in the gauge fixing condition. Theta appears only here.
What would the Gauss number of theta be?
I would guess 1. So pretty much I can just integrate away theta and pull down this to get bi, dif here. And let me put the dt here. So see, in our quantum field theory situations, typically G, B, B, C are fields, right? So I want to keep my my path integral in the standard form. But these extra parameters are typically going to be just some finite dimensional set of parameters. So I don't really need to go to the great lengths of having actually ghosts for them. I just introduce them for a moment, but I get rid of them immediately. What I'm left with is this. So the idea is that when you do BRST quantization with some gauge fixing conditions which depend on parameters, your integral over you have some integral over the parameters, and you need some measure to integrate. Because, I mean, you want something that is not depending on the specific way you parameterized, for example. And this measure is provided by this sort of ghost insertions. So you insert one of these things for each of your parameters. So because of that, when you define the most general scattering amplitude of string theory, suppose you want to do some complicated scattering amplitude, even in, it loops. So it has some integral over the moduli space of complex structures, or over the possible choices of reference metric. So it has some big families of reference metric that you use for gauge fixing. I think at some point we denoted them like this. Mu are some parameters. And your amplitude will be an integral over this sort of families of metrics. With measures. So the gauge fixing condition, remember, was just B, AB. No. Sorry. Let me just, I'm not going into details because I'm not going to use it. I just want to mention the formula. So you get something like this. Insertions of B, AB, dH, AB over d mu. Okay. And then you get your vertex operators, typically written as because they come from that represent the incoming strings. And all this is computed as a correlation function for your fields on the worksheet. So there is some Riemann surface with one hole for each, a generalized donut with one hole for each loop, and one operator insertion for each external string state coming in, with reference metric. So this is the final form of this thing I promised you at the beginning of the course when I said the amplitudes of string theory are a sum of all the possible topologies, which simply means the number of holes, number of loops, some coupling. And then an integral over the shape or the intrinsic geometry of this worksheet. And an integral over.
Real quick, is that a product over the news or the sum over the news? Like the space limit index?
Where?
So you have DH total A B D U new and then D for I think that's new. Like is that an implied sum?
Yes, yes. Well, no, that's right. Sorry. So this is just a product over U. See, because the B's are actually Grassmann odd, when you do this product, the B's are antisymmetric. So this thing is actually like determinant. You could write this as a product of B's times the determinant of this times the product of the mu's. Mm-hmm.
You know, the more holes that you have, the smaller it is, so that sum is finite eventually.
It's a perturbative series. So back in quantum field theory.
That multiplies.
Yes. So I put here some coupling, the number of loops.
Oh, I see.
So there's a theorem that all the two-dimensional surfaces, the topology of these two-dimensional complex surfaces is characterized by the number of handles, the number of loops. So while in quantum field theory there will be many different topologies of a Feynman diagram, all these different topologies look like one object in string theory. So let me just give a few examples. Say for a scattering of 4 particles, in quantum field theory, you might write things like this, or like this. But in string theory, you only have one diagram. Which is described as a sphere with 4 punctures. On the other hand, if you're looking at one loop diagram, again, in quantum field theory, you could have all sorts of things. You have something like this. I don't know. Maybe something like this. And many others. In string theory, you only have a diagram which looks like this. Again, I cannot really draw it properly, but these are supposed to be tubes. So this corresponds to a donut with 4 punctures. And so on and so forth. If you have a Feynman diagram which has 2 loops, this might look like a pretzel, something like that. A surface with 2 holes and 4 punctures. Mm-hmm.
I'm a little confused about the notation for the amplitude. What all
Yes.
the symbols are. So you have a product over U.
Yes. So right. So there will be these surfaces will have some matrix. So up to Weyl transformations and diffeomorphisms, I can characterize them by a certain finite dimensional family of matrix. So I have some number of parameters. This number of parameters is actually 3 times the loops minus 3, the number of mu's. Plus the number of points. On the surface. So here you need one of these factors for each parameter. Actually, sorry, this is a number of complex parameters. So multiply that by 2 for the real parameters. So here is a product of u goes from 1 to the number of parameters, to the number of mu's. So for each parameter, this gives you the product of all these factors gives you a measure on the space of parameters. And it is to say that if you reparameterize this space because of these derivatives, everything remains well defined. This gives you a Jacobian that cancels the Jacobian for this. Okay. So as I was saying, this formula has many ingredients. There is a correlation function for these theories of 3 scalars and for the ghosts, which, morally speaking, is like the path integral over all possible ways your worksheet can be embedded in space-time. There is an integral over all the possible intrinsic geometries of this worksheet, and there is a sum over all the topologies of the worksheet. This is a perturbative expression. It's a perturbation theory. Won't converge. And the calculations become complicated as the number of loops increase, because the moduli space, the space of possible parameters for a surface with a lot of loops is actually a pretty complicated space. But people, I think that in superstrings, people have done calculations up to 3 loops. It's an heroic effort. It's probably possible to do more, but it's also not particularly instructive, perhaps. The beauty of string theory, which sort of we barely managed to scratch next week, is that there is actually a lot of non-perturbative information hidden inside perturbation series. So when we start introducing things like D-branes, we start seeing non-perturbative information pop out without actually knowing how to define string theory non-perturbatively. Okay, so this is a pretty complicated, not actually, it's not that complicated looking. All the ingredients here can be made extremely precise. You can patiently pick some parameterization of the matrix, compute this, and then this is all geometry, okay? There is nothing deep. It's just geometry of 2-dimensional surfaces. And then you're left with some free field theory calculation for the Gauss and the scalar fields over these Riemann surfaces, and with some integral. It's kind of astonishing that the tools you need are so simple, and then you still get a very rich and beautiful theory. Now, for our purposes, we will only do 3-level diagrams. So the only degrees of freedom are really the positions of these points. And there is a little trick that is quite useful. That is that a lot of these B's and C insertions can actually be canceled out against each other. So when you do 3-level amplitudes, the formula you need to use is much simpler than this, and I'll write it in a moment. The only last observation I want to do is that it's kind of entertaining that if you count the number of B's and the number of C's here, it turns out, so they're not the same. The difference between the two numbers is exactly the anomaly for the ghost number current. So here you have exactly the right numbers of B's and C's to get something that is non-zero. Now, this is not a miracle. It has to do with the fact that these sort of insertions are trying to get rid of some zero modes for the B's and for the C's. And the zero modes are also what causes the anomaly. Anyway, so for 3-level amplitudes, we need less. So for 3-level amplitudes, if you work in a conformal gauge, and so your mu's coincide with the positions of the puncture. So the only information about the shape of the surface is the actual position of the punctures. Well, an expression looks like this. So if you remember yesterday, I mentioned that on the sphere there are, even after you fix the conformal gauge, after you fix the metric to be flat, there are still some holomorphic coordinate transformations which are globally defined and can be written like this. These transformations have 3 degrees of freedom because you can, although there are 4 numbers here, you can always multiply numerator and denominator for the same thing. So you can always use these 3 degrees of freedom to move 3 of your punctures wherever you want. That's why yesterday, actually, we had to do no integral. We had an amplitude involving 3 particles, and I said we can always map whatever Riemann surface with 3 tubes down to a sphere with 3 punctures at the position I decide. But if you have 4 tubes, say, your diffeomorphisms and wild transformations are enough to fix 3 of the positions or the punctures where you want, and the 4th one is somewhere, and you don't know where, and so on. So the first 3 particles sit wherever you want to put them. Sorry. The other particles sit wherever they want. So we had to integrate over the position of these particles because those are intrinsic, that's the intrinsic geometry of this surface. And it turns out that the B ghosts can be used to exactly cancel out the C ghosts from them. So you just have a product of V K, ZK, the ZK, the Z bar K, K equal to 4 all the way to N. So this is the answer for string theory 3-level amplitude. Now let's see if it makes sense. Yesterday we mentioned that the way operators transform is controlled by the eigenvalues of L naught and L naught bar. One way to say this is that if you want the combination of the z to the delta, the z bar to the delta bar is constant. Sorry, of course, this was the z tilde. This is the z. So in particular, the vertex operators have, after you strip the ghosts, have L naught and L bar equal to 1. So this is well defined. This is invariant under changes of coordinates. So this is good. Now you might wonder what about the BRT symmetry of this object, because we said, when you do BRT quantization, you're supposed to only work with Q-closed things. These were our Q-closed things. But after I strip the ghosts, these ones are not Q-closed anymore. So you could worry. But actually, it turns out that these guys are Q-closed up to a total derivative. Which means that because you're integrating over these variables, as the case, even if you insert something that is Q exact here, you try to move the Q around on the other operators, it will not kill them, but it will give a total derivative, which will integrate to 0. Hopefully. This is almost true. There are some, if you remember in quantum field theory, there are things called infrared divergences. And they're property of low energy, the property of quantum field theory at low energy. So because string theory reduces to quantum field theory at low energy, string theory also has infrared divergences. And they do manifest themselves into string amplitudes. And the way they manifest themselves is by subtle violations of these statements that I just made. We're not going to go there, but I just wanted to mention. OK, so we're ready. We can compute it for the scattering of 2 tachyons to 2 tachyons. I want 4 tachyons coming in. The momenta P1, P2, P3, P4. So we have the usual ghosts. Correlation function, which gives us and then we have the correlation function of 4 vertex operators. Which gives a nice delta function of the momentum conservations. And then this product of Zi minus Zj to the Pi dot Pj. Okay. So let's put the pieces together. So let me first collect the things that depend only on the first three coordinates. There's a contribution from the ghosts and a contribution from the scalar fields. And then I have an integral of the position of the last puncture. Let me just call it z. Okay. That's it. Not so bad. So first of all, does this make sense? This integral. What can go wrong? It can go wrong at infinity. It can go wrong when z hits the zi's. Remember that we have momentum conservation, and these are all tachyons. Particularly the behavior at infinity of this is like z to the 2 before sum of pi, which is z to the minus 2 before squared, which is z to the minus 4. So this integral definitely converges as infinity. That's fine. What about when z hits the zi? Well, this sort of integral, the square z 1 over z to the alpha, which in polar coordinates is something like r dr over r to the alpha. So this is fine if alpha minus 1 is smaller than 1. So here we need, for convergence, sorry, minus 2. I can also write this condition as before plus pi squared greater than or equal to 2. Now, where does this condition come from? Well, let's go back here. Go back to this diagram. Suppose I'm doing the same calculation in field theory. So some P1, P2, P3, P4. So the momentum that propagates in intermediate channel is something like P1 plus P4. Now remember that the string theory calculations are analogous to the calculation of quantum field theory made in the proper time formalism. So this sort of propagator was represented at this sort of integral. Okay. Sorry, I don't have much space. So because I decided we use this Euclidean over time, this integral here actually makes sense as an actual integral only if the exponent is negative. Okay. Otherwise, this integral does not converge. Of course, it can be defined, once it's defined for these values, it can be defined everywhere else by analytic continuation. Okay. Alternatively, one can use a Lorentzian proper time and look at an integral like this. Which also includes the I-epsilon prescription. So, because the intermediate part, the first intermediate particle you get in this sort of scattering of tachyons is also a tachyon, which has m square mass minus 2. It's not surprising that we get this sort of condition. So, you can look at these two ways. One is that you look at this integral, you compute it in a regime where this holds for all the momenta, and then you analytically continue away from there. Or you adjust your integration contour. You do a weak rotation here, analogous to this weak rotation from tau to t. This weak rotation essentially can be done by, so this starts its life as an integral where the z the z bar. And z bar equals z star. But if you just look at the integrand, it's completely homomorphic both in z and in z bar separately. So you can in principle treat z and z bar as independent coordinates. You can look at this as a contour integral, an integral in sort of middle dimensional submanifold inside z and z bar defined by this condition. And then you can take this integration contour and move it around. Sort of weak rotate it. Indeed, more or less speaking, z, well, okay, I'll discuss this maybe a little bit later, more detail. But so that's how you introduce things like I-epsilon prescriptions. Instead here, you start with sort of standard integral, and you start analytically continuing it away from this integration contour. And in the process, you can actually make it convergent away from this region. Let's just do it in the standard way. We start from this region, and now we need to do this integral. It's perfectly well-defined, convergent integral. Also tough looking. Now, also another thing you can observe, it looks like this depends on the Z1, Z2, and Z3 coordinates. You remember the dependence dropped out when we scattered 3 particles. It would be nice to see it drop out here too. Now we can do a change of coordinates. Let me define the coordinate t as z minus z1 over z minus z3 times z2 minus z3 over z2 minus z1. Now I didn't get this coordinate out of my hat. This is actually a useful object. Is called the cross ratio, and it's useful because it's invariant under the sort of transformations up there in the upright corner. So if you do this coordinate transformation by hand or with Mathematica, the final result is this. So the dependence on Z1, Z2, and Z3 actually does drop out. Now, this looks like a two-dimensional version of the beta integral. I don't know if you've ever seen that. And indeed, it can be computed out of the beta integral. if you use some tricks based on the Riemann bilinear identity. Alternatively, you can compute this by using formula like t to the alpha equal integral of e to the minus s t t squared s to some power, and then so that you bring these things to exponent, complete the squares, do the t integral, and then the s integrals. Let me just give the answer here. Okay, this is the Virasoro-Shapiro amplitude. Now let's pause for a bit and stare at this expression for a while. So, first of all, this expression is supposed to take into account all possible processes in string theory where at tree level two tachyons come in and two tachyons come out, which means actually, let me just use that. That if you look at string theory as a quantum field theory with infinitely many fields, this amplitude is supposed to account for all the processes which look like this. Where the wiggle can be any string state. Somehow this expression has to be capturing scattering amplitudes involving any possible of the infinitely many particles which can propagate in string theory. And it should include S, U, T, and U channel for all of those. So let's see if that's plausible. In quantum field theory, you recognize a diagram like this because you see the effect of the propagator. So a diagram like this gives you something like 1 over 1 plus P4 squared plus mass of this intermediate state squared. So perhaps you should start looking at the poles as a function of P1 plus P4 squared. And remember that P1 plus P4 squared is just 4 plus 2 P1 dot P2. Well, this expression here definitely has a lot of poles because there are gamma matrices, sorry, gamma functions. There are poles from this gamma function, poles from this gamma function, poles from this gamma function. Where are they? The gamma function has poles at 0, minus 1, minus 2, minus 3, minus 4. So that means 1 plus P4 dot P1 equal to 0, plus 1, plus 2, plus 3. Which means P1 plus P2 P4 squared equal 2, 0, minus 2, minus 4, minus 6. Now these are exactly the masses we found for the string modes. first. This expression need manages to have poles at all the correct places in the S channel from this gamma function, T and U channels. Now, what are the residues of these poles? So how does this function behave near these poles? So suppose I want to compute the residue at P4.P1 equal to minus n. So these and these just contribute some number, some function of n. For example, this gives you n factorial. And this, I think the residue of that is also 1 over n factorial. Let me see if I remember. I think so. So the residue starts with something like 1 over n factorial squared or something like that. Doesn't matter. But what matters is the rest. So you get gamma of 1 plus P4 over P2 over gamma of, let me start now use momentum conservation. Okay, sum of Pi equal to 2. That allows me to write this in terms of P4 dot P2. So I get 2 minus n plus P4 dot P2, and then gamma of 1 plus 4 dot P3 over gamma of 2 minus n plus P4 dot P3. Now these ratios of gammas are very nice because they actually simplify a lot. Remember, the gamma function satisfies gamma of x plus 1 equal to x gamma of x. So this is actually the same as this. Which means that the residues are polynomials in the momenta of order n minus 2 and minus 1. So if I'm looking at the intermediate channel, which is a tachyon, for example, this is just a number, degree 0. If I look at the intermediate channel, which is a graviton, I get degree 2, and so on and so forth. Now, this makes sense. If you look at the Feynman diagram for scattering to a graviton in intermediate channel, you get a second power of the momenta there. So in general, roughly, if you exchange a particle of spin s, you expect to see something like 1 plus P4 squared plus the mass of the particle squared, and then to see some polynomial of degree s in the momentum. And this is what we find here. So indeed, the string states at level s are built out of 2s oscillators on the scalar field. In particular, you have a minus 1. You can use s a minus 1s and s a bar minus 1s. So you typically have 2s Lorentz indices. There's something else being 2s. Okay, so the residues of this amplitude look good. Looks like it's really representing standard scattering processes. In particular, if you look at this amplitude looks like it's going to satisfy things like unitarity. So it satisfies the basic axioms that scattering amplitudes in quantum field theory have to satisfy. And this beautiful fact we'll keep going through at loops too. So it really defines a consistent theory, at least in perturbation theory. Now, although this, as I was saying, the contribution at each residue really resembles quantum field theory, that doesn't mean that that's quantum field theory. So you can see that the difference between quantum field theory and string theory. Sorry. Most sharply. I guess I just can't win. Sorry. I guess I'll take this one. So, if you study processes which probe the internal structure of your strings, so suppose you take two particles, two taxons coming in at very high energy. And then scattering off at some angle, some finite angle. So this is a regime where P4 plus Pi squared goes to infinity, but the ratios are kept constant and depend on this angle. Now, it's common to describe things in terms of Mandelstam variables, which are just so this was actually U, I think. It's not a notation. This is S. So you can ask what happens if all of these go to infinity. No, the arguments of the gamma functions go to infinity. Now, remember that the gamma function is like factorial. So the asymptotic of the gamma functions is like the asymptotic to the factorial, like in the Stirling formula. Remember, e to the n log n. So it turns out that this amplitude is actually very, very small, exponentially small in this regime. So while scattering amplitudes in field theory tend to behave like powers in this regime, and in particular powers which actually grow quite fast if you have particles of higher spin, like gravitons. The amplitudes for strings decrease very fast. Because when you smash strings together very hard, you start seeing that they're actually fluffy objects. They're not point particles. And this fluffiness is the Fourier transform of this exponential decay. So this is how string theory manages simultaneously to have particles of high spin, like the gravity, in particular to have gravity, without having the fast grow at high energy of scattering amplitudes, which is part of the reason UV, theories of gravity have UV problems. Now, I did the calculation here for tachyons. Again, it's straightforward to do it for other particles, say, compute the scattering of gravitons. It's just a matter of patience with combinatorics. But actually, it's not as much patience as you need in quantum field theory. So if you try to compute scattering amplitudes of gravitons in quantum field theory, you get gazillion Feynman diagrams. And the combinatorics of this kind of calculation is actually much simpler. And so this sort of observation was the original motivation of a certain line of research in gauge theory and in gravity, which shows that Feynman diagrams are actually not a good way to compute things. There are much more efficient ways to compute scattering amplitudes. And it's a program that has been quite blooming in the last few years. Now, so in principle, I could start from this, compute a lot of scattering amplitudes, and then patiently write down an effective action for those and figure out what is the effective action for, say, the graviton in string theory. I would expect to recover Einstein's gravity, because more or less it's almost a theorem that you're going to recover that in quantum field theory. But it's surely going to be very laborious to do it like that, one scattering amplitude at a time. So in the next lecture, we're going to see an alternative way to derive the effective action for the string modes.